Fantastic. So I'm going to briefly introduce, partly to motivate the talk, the QUT Centre for Robotics, which I'm fortunate to lead, introduce our group and what we do, talk a little bit about what we do, and then I want to talk about three key insights we've derived over the last few years in particular in our journey to push robots, in particular robot sensing and localization systems, into a variety of really extreme, very challenging environments and what we've learned. All errors are not equal. We need better metrics and the incredible power of introspection. So let's start with introductions. So I'm fortunate to currently lead a centre in Australia, in Brisbane, called the QUT Centre for Robotics. We're a large, typical university research centre. We do fundamental and blue sky research, as well as applied and commercial and government research in just about every domain: the skies, the earth, underneath the earth, and in the oceans. So you can see a snapshot of some of the many projects, and I'm going to use some of these projects to, I guess, motivate three of the key insights that I'd like to spend a little bit of time diving into in this quest to deploy reliable autonomous systems in a range of challenging, mostly terrestrial and sub-terrestrial environments. One thing that our centre has particular expertise is, and you'll probably find this from a number of the Australian robotics centres that are talking today, we do a lot of blue sky research, but we have a lot of experience fielding these systems in really challenging deployed commercial circumstances. And that is really, really difficult to do, and you learn a lot painfully along the way in doing so to actually get systems that are reliable enough to last for long periods of time in the field. Just to stimulate the discussion a bit, and I think Stefan will talk extensively about perhaps marine robotics later on. I don't want to preempt what you're going to talk about, Stefan. This is two projects in the marine robotics space, one of many, many projects in our centre. This is QUT. QUT is Crown of Thorns Starfish. It's an acronym. This is an invasive species on the Great Barrier Reef, which is one of our big natural wonders of the world. And a team at QUT and associated institutions developed back then state-of-the-art deep learning algorithms to run through the computer vision systems that that robot had to identify safely, with lots of redundancy and safety checks involved, the Crown of Thorns starfish, to identify it and then stab it to death with a big syringe, which is that long appendage you can see there. That really captured the public's imagination internationally as well, and so a number of organizations gave us a stack of funding, including Google, to develop a fleet of ranger bots, which are deployed all around the world, as well as surface-based craft. And these craft are operating in what you'd consider relatively extreme environments. The visual conditions are sometimes very, very challenging, and so you learn a lot from the process of deploying that. And so this is Serena and Professor Matthew Dunbarton and a cast of many people involved in this work back in Australia. The other environments that we work in are the other end of the extreme. So the two premier destinations for researchers in our lab are the Great Barrier Reef or Antarctica. And so we have a team of researchers who have just got back from their second season of operating drones in Antarctica for a major Australian project. Again, this is a very challenging, very extreme terrestrial environment. And apart from simple things like heating your batteries, you learn a lot about the perception and localization system reliability you need to operate autonomous systems and semi-autonomous systems in these environments. So we have a lot of real-world experience that is backing a lot of these insights. The group I'm fortunate to lead within the centre is really focused on positioning for autonomy, scaling up in time and space. And so this is a nice overview graph that I show, which is very unscientific because each axis has two different variables associated with it, which are confounded together in order to fit this into a 2D visual. But basically on the left vertical axis, you have time scale and temporal latency, so how responsive the system is. And on the bottom scale, you have spatial scale and or precision. So we're working on global alternatives to GPS, which is right on the top right of the spectrum. We're working on positioning systems for surgical robotics, which is right at the left side of the system in terms of high spatial precision, and then a range of projects in autonomous vehicles and related fields which span throughout the graph. Once again, this diversity of experience gives you a lot of experience in learning what works and doesn't work when you actually want the system to work in the real world. Two of the challenges that we've really focused all of our research on over the last 2 decades is really these dual tyrannies or dual challenges of viewpoint and appearance variation in the context of localization. But these would also apply to robots that are doing object recognition, segmentation, any sort of perception task. So the world is always changing. Seasons change, weather changes, atmospheric changes, the structure of cities change. Everything in the world, or just about everything in the world, is constantly changing. This is very challenging, as we all know, for autonomous systems. So a huge range of challenges there. And the core appearance challenge is encapsulated in this figure. The two pictures on the left are the same location in the world. The two pictures in the middle are different locations in the world, and you can immediately grasp that this is not a trivial problem, even for today's state-of-the-art visual perception and localization systems. The other challenge of many, but these are the two challenges we focus on, is viewpoint change. So if you have robots navigating, doing useful things in an environment, they are not always visiting the environment from the same perspective along exactly the same path with the same roll, pitch, yaw. They are experiencing the environment from a variety of not always consistent poses. And that creates an additional problem for your perception systems in a context like localization. And if you put them all together, I like to use the overused landmarks in my talk, so the Eiffel Tower is a good one. If you put both appearance change and viewpoint change together in the context of, say, localization or landmark-based localization, this is a very hard problem, and we still have a long way to go to solve this completely robustly in all applications. The other aside I want to note is that I've phrased this as viewpoint invariance and appearance invariance being the ultimate goal, but of course it's not the ultimate goal always. So for your robot systems, for your autonomous vehicles, for your drones, sometimes you want your systems that are doing localization to have high degrees of viewpoint sensitivity and high degrees of sensitivity to appearance change. You do not always want your perception and localization systems to be invariant to everything, because sometimes that sensitivity and that discrimination is very useful. For example, for telling you which lane you are along a road and which side of a two-way road you're on. So it really depends on the context, and that comes back to one of the key insights I want to share a little later in this talk. So we do a lot of work in this space. We draw heavily on biology. I think there's a lot of insights to take from biology in the context of perception and navigation, multi-agent teaming in extreme environments. We know there are biological examples aplenty, and so we draw a lot of inspiration from biology and neuroscience in doing our work. And the work that we initially were most well known for is some of the large-scale vision-only mapping SLAM localization experiments, both long-term indoor experiments and at the time the largest outdoor environment that had been mapped by a vision-only SLAM system, which was rapidly surpassed by Oxford and then a number of other groups, but we had the record, I think, for about a year and a half. But these were not in challenging environmental conditions. As we started to work with industry partners more and more, we discovered that, of course, these ideal conditions are not what our robots face in the real world. Our robots face much more challenging, much more extreme conditions in most environments outside of an office or a suburban street in sunny Australia or sunny California, which is always the joke told about why autonomous vehicle companies choose to test in certain locations. So these insights that I'm just about to go into have been driven by a lot of more translational work, a lot of more applied work where we take these amazing state-of-the-art research systems, both our own and those of others, adapt them and put them on robot systems. And of course, they never work the first time, the second time, often 10 or 20 iterations later, they're still not working at a sufficient degree of reliability. And it's that interesting cycle of iteration and feedback from what we call real-world testing that is really interesting to learn from. All right, so I spent less than 10 minutes talking about the core research we actually do. Now I get to spend the bulk of the talk talking about 3 points that I think are particularly important to the context of what many of the talks are today. So, as I said before, I'm going to motivate, these are not hypothetical, I have not made these up. These are things that have come up time and time again in trying to deploy research-grade perception and localization and sensing systems on robots and autonomous systems of all varieties that need to actually work in unconstrained, often uncontrolled, real-world environments. And these are, all errors are not equal. Conventional metrics are often not strongly predictive or completely unpredictive of actual deployment utility, so how useful they are actually in practice. And for operationally critical human, supervised, or multi-agent collaborative tasks, introspective capability for your autonomous systems in terms of single characteristics trumps just about every other characteristic you would want in terms of enhancing the utility of your systems. So I'm going to go into a little bit more satisfying, hopefully satisfying detail on those and motivate them. And I'm going to use real industry projects that we've worked on, along with all the research that we've done along with those projects, to try and provide some detailed context. So let's start with all errors and sensors are not equal. So this is a project that we worked on with the Queensland government back home, other companies including Mining 3 and OEM supplier Caterpillar, one of the largest machinery equipment suppliers of this type. So the only arena in which autonomous vehicles have actually been deployed in the long term in a commercially viable manner is mining. We have lots of pilot trials of robo-taxis on the roads, but this is one of the areas where the critical viability of large-scale industry is actually reliant for real on autonomy and limited levels of autonomy. And a lot of this has been happening in Australia. We've come to this just in the last few years, but some of my colleagues worked on a lot of the pioneering autonomy tech for these vehicles many, many years ago. For this project, we were tasked with creating 2 perception and localization systems, including the hardware layout or system, for autonomous load haul dump trucks or LHD trucks. These are trucks that operate underground. They are the workhorse of basically digging up dirt and moving it from one place to the other. And so much of modern society, every piece of electronics we rely on and take for granted, is critically dependent on the work that these vehicles do. This is a load haul dump truck. These can be 10, 20, 30 tons. Many of these already have some degree of autonomy or autonomy combined with remote operation. These are some of the images from the many sets of trials we did in underground mine sites around Australia. This is the custom sensor rig that we developed at the front. The inset photo shows you how challenging these environments are. So you hear people coming back with then $100,000 LiDAR sensors that have been smashed by rocks as quite a common occurrence. So it's a very, very challenging environment. It gets very dusty, things get wet. The lighting conditions are very challenging as well. So I'm going to work backwards from what we actually did. So this is one of the final handovers that we gave to our industry partners. This is our system localizing within a 5 to 10 kilometre journey deep underground, up to 600 metres underground in a mine site. You can see the vision flow from the top right. We also had a 2D LiDAR sensor as well. And you can see it keeping track of where it is in the mine site on this corkscrewing journey up to 600 metres deep underground. And if you ever get the chance to go down into one of these mine sites, I thoroughly recommend it, because they take you down and then they turn the engine off and then they turn all the lights out and you immediately freak out. It's a very surreal experience being hundreds of meters underground in pitch black. So we learn a lot of things that in retrospect are really blatantly obvious. So the first was not all errors are created equal. So these are overhead views of the tunnel. The tunnel is the blue dots on the side, and we're talking about the composition or components of error for that vehicle. So the Euclidean area is the total XY distance error, as if you're looking down on the robot or the vehicle from above. But you can split that into 2 components. Downtrack error, which is when you're going down a 100, 500 meter long tunnel, your uncertainty in how far along that tunnel you are. And then there's lateral error or cross-track error, which is your uncertainty in how far you are to the left, close to the left wall or the right wall of the tunnel. So most of the time, the lateral error is a far more important error to keep low than the longitudinal error, because most of the time you're somewhere along a very long tunnel and you don't actually care precisely where you are. You start to care precisely where you are longitudinally along the tunnel when you come up to a fork or a decision point. And so it becomes very important, but only at very specific points in time. The lateral error is generally very important because you have a very expensive vehicle going at high speed. There's a very unforgiving rock wall, half a meter or a meter or whatever to the left and right of the vehicle. If you get your lateral error wrong, not only do you risk damaging the vehicle, but you might shut down operations in the mine for a few days, especially if people have to go in and rescue or supervise rescuing the vehicle. And the costs there can be astronomical because mining is such an industry at scale. Not only are not all errors equal, but not all sensors have equal errors. So these are basically localization plots of the distribution of localization hypotheses. Once again, you're looking at the tunnel from above, and you're looking at the update from the laser on the left, and from the camera in the middle. And you can immediately see what you might intuitively expect. The laser is very good at locating you laterally, but in a long, geometrically featureless tunnel, it's not necessarily that good at telling you how far along that tunnel is, especially if the end of the tunnel is beyond the maximum range of the laser sensor. The camera is not so good at locating you, or the camera in the configuration we used it is not so good at locating you laterally, but it is very effective, more effective at locating you longitudinally. And if you combine them together, you get this nice complementary set of capabilities. So not only are not all errors equal, but obviously the errors that different sensors create are different as well. And so the takeaway from this is basically that the significance of different types of error in your sensing, perception, and localization systems is highly contextual. It has to be evaluated in the functional context of how you would deploy this system, not just on abstract benchmarks. And even then, that's not enough, because the significance of these different types of errors will vary from 1 second to the next massively for an autonomous vehicle in a mine site and many other applications. So that's insight number one, and we've done a lot of research following up on this. The second one, and probably you've already heard, it's the first day of ICRA, you've probably already heard someone rant about this, but this is really, we need better metrics. And once again, I'm going to illustrate it in the context of a real industry project that we were doing, testing on actual data from actual fleets. This is a project that we did with Ford Motor Corporation over the last two to 3 years. Again, we're working on sensing and positioning systems for autonomous vehicles. And again, if you want more details, there's publications all along the bottom of these slides. So if you publish in robotics, but particularly a localization paper in something like CVPR, you will typically have a table like this. So this is from one of our, I think our CVPR 2021 paper. And so you'll have all these standard metrics, recall at 1, recall at 5, recall at 10. If you don't put these metrics into your paper, you are almost certainly screwed at review time. They're sort of the de facto standards. But what we found was we were working on all these real-world projects with actual industry partners, and we were making significant functional improvements to our systems that we were developing for these partners, and it was not scratching or making any difference to all of the metrics you would normally report in a top conference paper. So this is an example from, again, this is not hypothetical, this is from actual projects. On the left, this is a 40-kilometer segment of autonomous vehicle driving. And each of those blue bars corresponds to a performance measure for a 1-kilometer segment in order along that traverse. This is, again, a localization problem. The number on the left on the axis 1 is the percentage of locations within each 1-kilometer traverse that were localized to 100% at the coverage of achieving a recall at a certain level of precision. And so you can see it varies a lot. And so what we were able to do is we were able to make all sorts of system changes, front-end changes that massively improve the performance of those worst-case 1-kilometer segments where the vehicle is not sufficiently localized 80% of the time. And we made huge improvements in those areas, and so we went, awesome, we're going to try and publish this. And so we ran it through all of the standard metrics you would be expected to have for a CVPR paper, and it didn't make any difference to those metrics. And so this sort of kicked us off on this little crusade to try and add some additional metrics. We're not saying these metrics are bad, but they're woefully insufficient by themselves. Here's an example of that. We're going to show you 2 scenarios of an autonomous vehicle, and these 2 scenarios have exactly the same localization performance based on standard metrics. You're going to tell me which scenario you think is better and why. This is scenario 1. Blue is well localized, red is not well localized. All right, I'm going to show you a second scenario that is indistinguishable in terms of conventional metrics. So this is scenario 2. And you need to tell me which scenario is better intuitively and why. All right, which scenario, who would go for scenario 1 as being better? All right, who would go for scenario 2 as being better? Okay, anyone want to hazard a guess why scenario 2 is better? There's multiple reasons. Yep. You go. So a larger number of shorter periods with bad localization. There's another key reason as well, which relates to the previous point I made. Yep. Yep, it's localized over and up to the crosswalk, which is probably, if you're going to pick anywhere to be well localized. There's other reasons as well, but basically these appear identical in terms of a lot of standard reported metrics. And so that's really our point, that the performance metrics that we use, again, need to be much better contextualized, the deployment of these systems and the functional way in which they're going to be used. All right, the last one I want to talk about is the incredible power of introspection. I think this is the most important, especially when you think about robots collaborating with people and robots collaborating with other robots. So again, I'm going to give you a scenario. We're picking a localization or sensing system for a fleet of autonomous vehicles that's going to operate all around the world. We have two choices. We have system one, which got a CVPR paper because it has the best percentage performance. It has a system that works 99.9% of the time, but it doesn't have an introspection capability. It doesn't know when it's struggling. We have a second system which was unfortunately rejected because it didn't have a high enough performance figure, but it knows when it's not working that it's not working 99% of that time. Which system would you prefer for an operationally and safety critical autonomous system? System two? Yep. And the basic fact of it is that using system one, you will unknowingly be making critical life and death decisions based on incorrect positional information 0.1% of the time. Using system two, this drops by an order of magnitude to 0.01%. And so even though the sticker value on it of the system one is much better, especially for a conference paper, system two is much better in practice. And again, we're trying to push towards more of the research and research rewards, recognizing the functional relevance, not just the sticker label performance. These are known as, these relate to all sorts of terms which are not the same and I don't have time to go into, but it's all about the fact that we want autonomous systems around us that collaborate with us and that we can trust. And we're doing a lot of work in this space, so I've just got some papers. I did send one more slide talking about what we're actually doing, where we have a system that assesses the performance of localization systems and vets them with an integrity monitor over the top. And you can develop the most simple of integrity monitors and massively improve the reliability and safety of your system. Why is knowing when you don't know significant? So your system can stop, it can fail safe, it can pull over to the side of the road. It can facilitate human-robot collaboration through better handoff in both directions. You know not to hand off to the autonomous system if the autonomous system knows that it doesn't know what it's doing, and if the autonomous system knows that it doesn't know what it's doing, it can hand off safely to the person as well. Same goes for multi-agent systems where all the systems are autonomous. The handover and redundancy between a fleet of vehicles or agents should depend on the fact that each one can assess how confident it is in what it's doing at that stage and whether it can take on more responsibility or not. It's also useful for all the things that we do as roboticists. If you know that you're struggling, you can stop, update your maps or whatever representations you're using. If you know you're really struggling, you can stop completely, take operations offline and go through a period of relearning from scratch. You have options available to you, but you only have those options if you know to go for them. And that is really the key aspect of introspection. Again, this is another example motivated again from an applied project. We're working on a number of surgical robotics research projects. And this one is a robot that is meant to do one thing and one thing very well. It's not going to replace the surgeon. It's going to do one thing, which is place the guide wire into the glenoid part of the bone in a shoulder replacement surgery and do that repeatedly, reliably, and with a very small pose and angular error. The human or the surgeon or the supervisor watching that cannot necessarily tell how well the robot's doing because the fact that the surgeon can't do this perfectly is evidence of that. And so if the system is able to self-report when it's struggling and when it's confident, you facilitate its collaboration with the surgeon. So yeah, knowing when you don't know, to me is arguably the single most important property that we want to imbue in all of these sensing and perception and localization systems, especially if we want to deploy these in the real world. So that's, I guess, 3 key insights that have really come up and that we're working on, and a lot of our research has pivoted to trying to address these key insights and trying to improve the way we do research. If you want to know any more about any of the research in this presentation, There's lots of slides and links to the various papers that we've done. We do a lot of other stuff in our centre and in our group. We are hiring, we're always recruiting. Actually, I've got a slide on that later. And we also would like to thank all of our industry and funding partners, and of course our centre and our research group. Just want to highlight a number of other things. So there's a workshop, debates work. I don't want to take anyone away from this workshop. There's a very vigorous, robust debates workshop happening in the North building. We had our first one this morning. There's 2 more today. We're holding a workshop on responsible robotics, trying to get the level of discourse and discussion about the responsibility of roboticists for what they do up. And so that is a workshop that's running all day today as well. Thank you for inviting me again to speak at this talk. And again, we're always recruiting. And with that, thank you very much, and I'm happy to take questions. That's a great question. So the question was, yeah, what's the role of uncertainty? So we are on a 10-step journey along with many of our colleagues, and properly integrating uncertainty into it is probably step 2, starts about step 2 or 3. We are at step 1. And so all that initial work that we did was almost ridiculously simple. So all we were doing was training things like support vector machines to do a binary classification on some abstraction of the output of a localization system, the intermediate feature vectors or whatever, and make a classification about whether it's working well or not working well. So you could not get more simple than that, and that was incredibly effective. So first of all, it reduced the rate of unknowingly having bad localization performance. But one of the other things it did, and this is how we were able to publish the work, was it instantly gave you state-of-the-art performance, because you were able to knock out a lot of the false positives with very little collateral damage. So you had a few extra false negatives, but you knocked out a lot of the false positives, which means on the benchmarks that I was just ranting about before, things like precision recall went through the roof. So that's to come, but we're not there yet.
Hello, thank you for the talk. I was very curious about the project on underground autonomous vehicles. It seems like a huge victory for robotics that it's actually working and deployed already. And I'm curious about like the scale and the open challenges of this project, like how many of these vehicles are actually completely autonomous, and are they completely autonomous, or is there a person on board as well with the vehicle? Thank you.
So that's a great question. And so just to reiterate, I think I made the point before, we've come along to this work in the last 5 or 6 years, but people have been working on this in Australia and other locations for many, many years before that. And so these autonomous vehicles have been operating both below ground and above ground for many years. They are doing autonomy to the degree that is economically sensible. So you would never make something completely autonomous without any ability to intervene remotely. And so there are people in an air-conditioned, for example, people in an air-conditioned remote room who can monitor these systems. They can intervene when necessary, or the systems can flag that they need help. And so it is a mixed autonomy mode with some level of supervision. And I think what they've learned in doing that, you can see has come out in some of the revelations about autonomous vehicle operations in San Francisco, and also cashierless shop and go stores that were in the news recently, where those companies have found the sweet spot, or the viable spot, is actually to have a certain level of remote supervision, remote flagging of operators when needed. I think in some of the on-road autonomous vehicles, that was every 2 to 5 miles or something. It was flagging that someone needed to check on them. It's the same thing with the mining vehicles, but that's enough for them to be economically viable, for them to make sense. Even if you don't care about autonomy or robots, you would still do it from an economic perspective.
Regarding the Antarctic drones project, you have mentioned the problems with batteries. This is clear. What other perception problems were there? Or?
So that's one of the many teams within our centre. but I know one of the issues is an issue that's plagued robotics for a long time, and it's, I think, what got the flying drone on Mars into trouble. So the ability of suitably textured surfaces, if you're operating over the water as well, reflections, transparency, all that sort of stuff is particularly challenging in those types of environments. And so I think that's a not fully solved problem. And again, these teams are interested in doing environmental monitoring, so they're not going to solve any problems they don't have to. So they will still rely on other sources of positioning information, but that would be part of the entire solution.
Hello, thank you again. Sure, thank you again for the presentation. I just wanted to ask regarding the integrity. You told us that you're already participating in how to assess the integrity of a system. Could you just give us some highlights about this, and especially since we need a lot of data in estimating the integrity of a system, at what stage simulated data can be used without biasing the integrity score? Thank you.
Oh, okay. Given the time limits, I don't think I can do justice to it. So we looked at simulated and augmented data, and within the resource constraints that we had, we didn't go down that route for developing the integrity monitor. In terms of the amount of training and the amount of data, I guess the one thing that's good about integrity monitor approaches, at least in our experience, has been it's not like fine-tuning visual features for a new localization benchmark. The quality and amount of data you need to make an integrity monitor that is significantly better than random chance is very minimal. And so you don't need particularly clean data, you don't need a large amount of data. As I was saying, we were using a support vector machine to do two-class classification on just the output of one of our localization systems. So it was very easy to get initial gains. I think the problems you allude to will come down in step 2 or 3 or 4, for example, if you properly integrate uncertainty, which we're not doing. I think they will become increasingly a problem, but they weren't a problem for us yet. Thank you.